to Priya Donti, who is a PhD student in computer science and public policy at Carnegie Mellon University and a graduate fellow at the US Department of Energy and Computational Science. We also speak to Lynn Kaack, postdoctoral researcher and lecturer in the Energy Politics Group at the ETH Zurich and member of the Austrian Council on Robotics and Artificial Intelligence, and David Rolnick, who is assistant professor in the School of Computer Science at McGill University and the Miller Quebec AI Institute. All three of them are chairs of Climate Change AI. Maybe to start with, I have some housekeeping remarks for you. So please note that this debate will actually be recorded and is currently live streamed to YouTube. You can find it afterwards as well on our YouTube channel. We take questions from the audience and you can submit them through the Q&A tool at the bottom of your screen. So that's how this works. And now we're going to dive right into the topic. So the use of digital technologies towards a sustainable economic transformation has become a key point of discussion in European policymaking. Recent breakthroughs in machine learning have raised hopes that artificial intelligence can bring us closer to achieving the United Nations Sustainable Development Goals. On the other hand, there are worries that AI or AI-based technologies can also become drivers of global resource consumption and emissions. Today's speakers are machine learning and policy experts from leading institutions in North America and Europe. They are committed to identifying and facilitating those uses for machine learning technologies that are actually beneficial for the climate and warning of those that might harm our planet. So with these introductory words, I hand the panel over to our distinguished speakers. Please go ahead with your presentation.
Yeah, hello. I'm going to start sharing. One moment. Sorry about that. All right, how's this?
This looks great.
Okay, great. So today we are going to talk about the intersection of artificial intelligence and climate change. And climate change has or is becoming an increasing threat to humanity and ecosystems. So we need climate change mitigation and adaptation strategies. Mitigation refers to reducing greenhouse gas emissions, and adaptation refers to adapting to the changing climate and its effects. The EU, for example, has an aim to reach net zero greenhouse gas emissions by 2050 as the mitigation strategy, in addition to many adaptation strategies. This is a fairly ambitious target, and I wanted to briefly show you what the emissions trajectory has looked like historically. So these are the total greenhouse gas emissions from the EU indexed by 1990. And we see they have been decreasing, but in past years, we can also see they have been relatively constant. And to reach net zero by 2050, we have a long way to go. And in particular, these last bits are much harder than what we've already achieved. So we need a whole broad range of approaches, and they need to address all sectors of the economy. And what we want to address today is how to align artificial intelligence with such climate change strategies. So what do we actually mean by artificial intelligence or AI? So generally, we can group any algorithm that allows a computer to perform a complex task. And typically, those complex tasks are associated with tasks that are close to what is regarded as human intelligence. Recently, a subfield of AI called machine learning has brought large improvements. So these are algorithms that automatically extract patterns from large amounts of data. So they learn patterns from those data. And such AI and machine learning algorithms are concerned with a variety of tasks of uses that they can be applied to. So for example, computer vision. Here, these algorithms can interpret the content of images automatically. The field of natural languages processing is concerned with parsing words and texts. Then such algorithms can also be used for time series analysis, so detecting and learning patterns and data over time and forecasting. And also there's a group of methods that's concerned with control that can then be used for operating complex systems. So for the intersection of artificial intelligence and climate change, we wanted to address 3 different aspects here. So we're going to go into detail into AI applications that are used for mitigation and adaptation. Then we also want to cover those AI applications that can increase emissions. And we will talk about the energy use of AI itself. And I will pass on to my colleague David Rolnick now to address those AI applications in mitigation and adaptation.
Thanks so much, Lynn. Let's get started with AI applications that can be useful in mitigation and adaptation. So there are a number of themes that we would like to highlight here. The first one is gathering information. So in many cases, there are large amounts of unstructured data out there that can't necessarily immediately be used to provide insights, but can be processed in such a way that there are insights for policymaking, decision-making. So for example, tracking greenhouse gas emissions in real time, pinpointing deforestation as it happens, and understanding infrastructure data, so where buildings are, where the electrical grid is in areas where we don't have access to that information. This is an example of insights that can be gained from unstructured data like satellite imagery and can in many cases be done automatically using AI. So I'd like to turn to one particular example here. So we'd like to highlight in particular the theme of improving food security. So the motivation here is that climate change is affecting agriculture in many ways by increased severity and frequency of storms, increased droughts, floods, and spread of pests and disease. And there is a need for monitoring yield of individual crops at scale. And there is the ability to do so using satellite and aerial imagery, which is increasingly available. But since there is a lot of such data and it is not really possible to do that, all that annotation and understanding that data by hand, it's really useful if it can be done automatically using computer vision algorithms from AI, which can, for example, automatically label crops over a wide area. You can see this being done in the figure for the country of Togo with an AI algorithm that is automatically labeling crops. So there are many different government programs that are working in this direction. For example, NASA Harvest in the US, the Copernicus Land Monitoring Service, in the EU, NGOs like GeoGlam and companies like Indigo Ag's Atlas Insights project. So the next overall theme that we'd like to highlight is forecasting. So understanding what's going to happen next, for example, in renewable energy supply, in addition to the demand for energy, transportation demand, and in some cases, forecasting extreme events. So I'd like to turn to a particular example here. And that is for nowcasting. The motivation here is that solar and wind power are variable sources of electricity, which vary based upon factors like weather. The amount of solar energy that you're generating is going to depend on whether the sun is behind clouds, for example. So forecasting power production is really necessary in order to help manage power grids and make sure that supply is matching demand and reducing the need for things like spinning reserve that would be consuming fossil fuels. So AI can be really useful here in time series algorithms that can learn patterns from historical data and weather in order to predict power generation. Many different players here. So Open Climate Fix, a nonprofit in the UK. You can see a picture of some of their data on the right-hand side, just indicating how all these little dots are indicating how much power is being produced by solar in the UK, and the clouds are influencing that. Also, the US Department of Energy and the National Center for Atmospheric Research have partnered to work on this in these directions. The next theme that we'd like to highlight is in improving operational efficiency, so making complicated systems more efficiently run. Often there are many different knobs that can be turned, metaphorically speaking, and AI can often be good at regulating all of those together in a more efficient way than a human might be able to do. So for example, in heating and cooling systems, in optimizing freight transport, and in reducing food waste by, for example, optimizing ordering systems for food to reduce the waste there. So to highlight a particular example here, I'd like to dive a bit more into HVAC, so heating, ventilation, and cooling systems. And HVAC systems account for over half of building energy use, and there's a lot of scope for making them more energy efficient. For example, by accounting for the building thermodynamics, usage patterns, and constraints with the equipment. And AI can really help here by, in many cases, learning efficient operational methods for automatically controlling HVAC systems. For example, with reinforcement learning, which is a set of techniques in AI, it is possible to much more efficiently control building HVAC systems so that the overall amount of energy and therefore the emissions are reduced. For example, DeepMind, which is a UK company associated with Google, has created an algorithm that has dramatically decreased the amount of energy needed to cool down Google's data centers. And there are also many applications in residential and commercial buildings. For example, the smart thermostat that you can see there on the right. The next theme that I'd like to highlight is in predictive maintenance. So in understanding failures as or before they occur. And this can be useful, for example, in preventing natural gas leaks in industrial settings, and in building more resilient infrastructure is increasingly necessary as the effects of climate change become more severe. So I'd like to particularly highlight an example here, which regards rail. So maintenance of rail systems. Obviously, rail is critical to decarbonizing both passenger and freight transportation. And predictive maintenance can increase the effectiveness and competitiveness of rail by improving the efficiency of the systems and reducing the need for costly repairs. So if something fails, it's much more costly than if you prevent it from failing in the first place. And AI can be really useful here in analyzing large amounts of sensor data at scale in order to detect anomalies that could be occurring in the future. And so, for example, as you can see on the right, Deutsche Bahn is using these automated technologies to analyze sensor data to understand failures of the railroad switches. Now, the next theme I'd like to highlight here is accelerating the process of scientific experimentation itself. For example, in the development of new materials for batteries and in clean energy materials like perovskites for photovoltaics or electrofuels. A particular example I'd like to highlight here is in energy storage and batteries. So the motivation here is obviously that batteries are really important to decarbonizing our energy systems. And there is a lot of R&D in the industry to improve both the performance and the cost of batteries and the need for new and more effective materials. And AI is not going to replace the function of scientific experimentation, but it can be useful in essentially automating some of the intuition to suggest new materials that it might be good to try. To speed up the process so that one has to try fewer candidate materials before one finds a good one. So there are many different players in this space. So for example, the Materials Project has a database of lots of materials properties that can be useful in AI systems. You can see on the right a figure from a paper using that to design better lithium-ion batteries. And there are many private players as well in this space that are looking to accelerate the process of scientific experimentation using AI for materials design. And then the final theme that we'd like to highlight here is in approximating time-intensive simulations. So for example, simulations in climate models, energy models, or various models associated with city planning, such as like wind flow through a city. And in many of these cases, there's a very time-intensive model that would take a lot of time, compute, energy to run, and AI can actually speed this up. So dialing into a particular example, we can look at climate models where there is a need for downscaling them. Yeah, great. So localized climate models. The motivation here is in modeling the climate. Obviously, modeling the climate and how it changes is really important. And making physics-based climate simulations somewhat less compute intensive, because often modeling the physics exactly is very possible, but it takes enormous supercomputers to run everything exactly. And so AI can be useful in coming up with fast approximations to particularly time-intensive bottlenecks within these models. And in particular, this can be useful in coming up with localized climate models, so climate models for particular localities, which would otherwise be prohibitively compute intensive to run. And AI can come up with a sort of quick and dirty approximation that means we don't have to run on these enormous supercomputers. There are many government agencies and institutes looking into this, for example, that institute in the US. And on the right, you can see a picture of automatic cloud monitoring by an AI system to feed that information into a climate model that can then be useful downstream. So with that, I'd like to turn it over to our colleague Priya Dondi, who will talk about the next components of our report.
Okay, so as we've heard, there are many, many different ways in which AI can facilitate climate action. But on the other hand, AI can be and has been used for applications that increase emissions, both through the immediate impacts of those applications and through system level effects induced by those applications. So going through each of these in a little more detail, I'd first like to highlight the use of AI for applications that directly increase emissions. So in particular, AI has been used for years in service of emissions-intensive industries, things like oil and gas and mining. And in general, what AI does here is it makes these processes in these industries cheaper or more efficient. And in doing so, it can, in some sense, impede the transition to cleaner or more climate-friendly alternatives by making these more carbon-intensive alternatives more competitive. So for instance, in a report from earlier this year called Oil in the Cloud, Greenpeace described the ways in which major tech companies such as Microsoft, Amazon, and Google are partnering with oil and gas companies to accelerate applications in that sector. And they're doing this both through the use of cloud computing technologies and also AI. So, oh, I'm hearing that there's some noise. Is this better? Okay. So focusing in on AI specifically, AI is being used to do advanced subsurface modeling to facilitate oil and gas exploration, to optimize drilling and pipelines in order to facilitate, extraction and transportation, and also to help with marketing to increase the sale of these technologies. And this unfortunately can have and has had very large impacts. So for instance, in case studies of particular projects, it was found that AI boosted productivity in those projects by as much as 5%. And on a macro scale, estimates by entities such as Accenture predict that AI could generate $425 billion US in value for the oil and gas sector by 2025. So these impacts are potentially quite large, but a challenge there is that they're often hard to measure, which then affects the way in which policy needs to approach regulating these effects. So in addition to AI applications that explicitly increase emissions like these ones, there are others with more uncertain or indirect impacts. So for example, AI is a key component of creating new technologies, things like autonomous vehicles and the shared economy. And diving into the picture of autonomous vehicles, for instance, the eventual emissions impacts that we'll see from autonomous vehicles are really potentially pulled in different directions by both micro and macro level factors. So on the one hand, autonomous vehicles may help reduce the energy consumed because by any particular drive, for instance, because they may be able to drive a particular vehicle in a more efficient way. But on the other hand, autonomous vehicles could potentially increase the demand for driving overall, for instance, by lowering the barriers to using individualized transport, which would shift demand away from public transportation options such as rail. And this might increase the overall energy assumed, and we often call these things rebound effects. So the overall impacts here are potentially unclear. So this is one type of uncertainty in terms of AI applications, uncertainty due to diverging effects that could go in different directions. But there are also other applications that are uncertain because they are so kind of long-term and systemic in nature. So for instance, one question that one might ask is, could AI drive overall increases in consumption due to its uses in applications like advertising? And in general, the impacts of these things are similarly very hard to measure. So far, we've focused on the impacts of applications of AI. And in addition, AI has energy impacts as well. So this is a conversation related to the one of the energy consumption of digitalization, which looks at the consumption of a whole host of technologies, including things like 5G, blockchain, edge computing, Internet of Things, and AI. So while these different technologies are often lumped together, understanding the energy impacts of these technologies separately from each other may also be useful in terms of targeting engineering and policy interventions in each of these areas. So in the case of AI, there isn't necessarily yet a macro level estimate that quantifies exactly the energy impact of AI, but we can start to get some proxies. So for example, the International Energy Agency, IEA, estimates that data centers consume about 1% of global electricity, and that this electricity demand is expected to remain roughly constant over time. And AI makes up some fraction of that. So given that this energy usage impact is through electricity, the greenhouse gas emissions then depend both on the electricity consumed, the total amount of electricity consumed, and also the carbon intensity of that electricity. And that means that there are a couple of different levers here, things that include increasing the efficiency of the uses themselves, of the algorithms themselves, and also the lever of cleaning up the electricity mix so that there's fewer emissions per unit of electricity used. So this is particularly focused here on the electricity use, and it's of course important to think about the hardware effects as well. So zooming in a bit from a macro level to an individual model level, the energy use of AI models is governed by a couple of different considerations. So first, what is important to understand is that there are different things that AI models use energy for. So one of these is training, the process of actually getting the model to learn patterns and data, and then inference, the process of then kind of applying these patterns that have been learned to do some kind of task. And these different stages have different energy implications, with training generally taking a lot more energy than inference. So when understanding this overall impact, it's important to note that AI is often thought of encompassing only very large models that can only run on supercomputers. But in reality, there's actually a very wide diversity of models here. So for example, a lot of models actually run in minutes on laptops. And these kinds of models are actually used very widely in many industries today. But on the other hand, there are indeed very large models that do exist, often in the realm of research. So for example, the model GPT-3 in natural language processing by OpenAI uses 175 billion parameters, so a very large model. So another factor to keep in mind, in addition to this sort of diversity of model size, is that models are often not trained from scratch. So for instance, some of these large natural language processing models are actually trained basically once, which is where the biggest energy use comes from. And they're used really widely with little additional marginal impact. So kind of understanding the actual training versus usage dynamics for any particular application can actually be really important in understanding the overall energy impacts of an AI algorithm. So to tie that all together, I wanted to use the example of Strubel et al., a paper that many of you may have seen that sort of quantifies the emissions impacts of large natural language processing models. The headline emissions estimates in that paper refer to the process of heavy experimentation in order to do research and build and construct and train some of the largest AI models from scratch. But the numbers on just training without the experimentation and the actual use of these models are much smaller. So it's important to sort of, again, understand the overall usage context when trying to think about quantifying the emissions of these particular models. So I'll close this part by saying that trends in this area should indeed continue to be monitored. And in some sense, the energy use of AI is actually one of the easier things that we've talked about in this presentation to measure. We can, instrument our equipment with measurement devices, for example, to actually measure power draw from a particular use of an algorithm. That said, while it's often tempting to focus attention on things that are easier to measure, regulation should indeed focus on the full systems context. So considering both the energy impacts of AI itself and the impacts of applications that AI is being used for to tackle climate change. And we actually anticipate that the latter, sort of the applications, both positive and negative, may actually have the larger impact. So I'm now going to actually hand it back to Lynn to talk a little more about this picture of policy and regulation.
Yeah, thank you, Priya. So I wanted to, in the last part of our talk, speak about what policy can do to align the use of AI with climate change strategies. And first of all, I wanted to bring up the ethics guidelines for trustworthy AI from the EU high-level expert group. And I wanted to emphasize that these considerations are really important also in the climate space. So AI applications need to be lawful, ethical, and robust. And those ethics guidelines also include some language around sustainability. So it says that AI systems should benefit all human beings, including future generations. It must hence be ensured that they are sustainable and environmentally friendly. And I wanted to go into a little more detail what that could mean. And we wanted to give some suggestions or ideas for policy directions that could be important. So in general, we distinguish two areas here for the policy considerations. So the first one is on research, development, and deployment of AI models to benefit the climate. The second one is on regulating AI-driven technologies. And the last one is on the AI use and data sharing in the public sector. So For the first part on AI research, development, and deployment, one really has to understand that one really needs to help the whole pipeline of AI applications in the climate change space. So this starts with research and ends with applying it in industry and in the public sector. So on the side of research, interdisciplinary and applied research involving computer science and machine learning and climate change relevant fields is really important. And those are fields that traditionally haven't had much interaction. So there's a lot to be done to bring people together and make them work together also really well. The second is that those ideas developed in research should be brought to the market. So we need to work on the technical readiness of these applications via R&D programs. And lastly, I wanted to also mention that there might be regulatory hurdles to deploying those AI strategies in the relevant sectors and industries, which should be addressed. And here it's also important to really carefully consider where AI approaches are actually appropriate and which other risks might come with them or cost burdens might come with them. So on the second part, I wanted to talk about the regulation of AI-driven technologies, and what we mean here is, for example, what Priya addressed, autonomous vehicles could be one example, or industrial applications. So it's important to incorporate those climate impact considerations into the regulation of these new and emerging technologies. At the same time, it's also really important to create economic incentives and regulatory requirements to reduce the greenhouse gas emissions from these technologies. And here really traditional climate change policy approaches are very appropriate, and they could help to avoid also rebound effects, for example, in industrial efficiency applications. And where applicable, there should also be mandates around transparency and reporting of greenhouse gas emissions from those AI applications. And that should also include life cycle impacts and externalities. And the last group of recommendations focuses on the use of AI in the public sector. And here we want to emphasize that it's really important to develop and enhance in-house AI capacity within public entities. Then a second point is that stakeholders, for example, from civil society, should be involved throughout the whole process of developing an AI approach, including scoping, design, and deployment of the models. This is really important to anticipate side effects really early on in the application development. Then there's also a tremendous need for standards and best practices for when and how AI should be used in the public sector. And lastly, we also encourage standards and good management around data collection, management, and sharing. Especially the public sector can have a supporting function here by providing machine readable and large data sets to research. So what we can see is that policy is really key for aligning AI with climate change strategies, and this addresses all three of these areas that we've touched on in our presentation. Please feel free to reach out at any point to each one of us here. Our email addresses are given. Also, please check out Climate Change AI if you're interested in finding out more about this topic. And this concludes our presentation. I'm really looking forward to your questions.
Thank you very much to all three of you. This was a really good and comprehensive presentation. I've learned a lot of things, and I think especially the last section is also very interesting for our viewers who are working in the European institution, because there is this special committee on AI in the digital age, and there's also legislation planned from the European Commission in the first quarter of next year. So maybe they'll take on board some of your policy recommendations. That would be great. So we've had 2 questions from the audience, and I'm gonna give you the first one. Do you see potential for reliable identification of extreme weather impacts relation to climate change in the context of loss and damage? And there was a follow-up question right afterwards. Can the algorithms be strong enough to trust such decisions? Whoever would like to answer that, just go ahead.
Yeah, so I can start, which is to say that there are, I think, a lot of different both data collection efforts and climate modeling efforts that can be facilitated or supported by AI. So these include some of the things that David was mentioning about, for example, using satellite imagery to monitor or understand various climate variables, or use AI to speed up various climate models in order to help make more localized predictions. But in all of these cases, it's really important to note that, you know, AI here is being used as a decision support. So for instance, if we are collecting information using satellite imagery, that's not necessarily going to be as good as data that is collected with on-the-ground sensors or more targeted data collection mechanisms. And it necessarily is not necessarily going to 100% perfectly predict the future. And so in general, it's worth understanding sort of what is the limitation of my prediction at this particular moment? What is the limitation of my assessment coming from an AI model? And sort of use that to inform the decision, in addition with other information as well, but not necessarily to dictate the decision overall.
Thank you very much for that, Priya. And there was a second question earlier on that one of you already answered in written. Maybe can we just repeat that and come back to that one, please?
It was a question about why are we using AI to increase the emissions of emitting sectors like the oil industry in the context of climate change when we should be trying to reduce these emissions. And absolutely, we agree this was included under examples of negative impact applications. So there are applications of AI that lead to positive impacts in mitigation and adaptation. There are applications that lead either indirectly or directly to negative impacts, and this was under those. We're certainly not suggesting that be increased. We're suggesting that it be diminished.
Okay, thank you very much for this clarification. That was just a misunderstanding, but it's good that we sorted that out. So we have 2 other questions for now. Do you have any thoughts on policy and systemic ways to motivate, now the question disappeared, AI talent, so students, data scientists, etc., to apply their talent to climate change related problems?
Yeah. David, do you want to talk about this? Because
sure.
We funded an org because of that.
Yeah, so we one of the key systemic issues here is lack of communication between different stakeholders. So lack of communication between people with AI skills and people in policy or people with climate change relevant expertise. And we think this is really critical. This is one of the reasons why our organization Climate Change AI exists, to really facilitate discourse, bring people together to talk in an informed way, learn from each other, and make sure that whatever is being done in a way that is cognizant of the many interests and many stakeholders involved. It's a much deeper question than that. There's a lot that can be done internally in the field of AI as well. But I think that the discourse bringing people together and as we mentioned, facilitating in-house talent is really important. Anyone else feel free to weigh in there too.
Yeah, so I guess on that point, if you are sort of one of those folks who is interested in sort of being part of this development, meeting other people in this particular space, etc. We, for example, are going to be holding a workshop in about a week virtually that I would encourage you to check out, in addition to some of the other resources on the Climate Change AI website.
So this is at one of the largest AI conferences in the world. I mean, it's a particularly policy-focused workshop on climate change and policy in the context of AI.
Thank you very much. And I think there's a direct follow-up question on this one by Ornella Xelili. What advice would you have for AI professionals who would like to use their skills for decreasing CO2 emissions and are new to the field?
Yeah, maybe I can jump in here. So climate change mitigation and adaptation is actually a lot of different fields, which is probably the first thing to know. So picking an aspect of it, like a field, for example, transportation, that you are particularly interested in and diving deeper into ways that you could help to reduce CO2 emissions from that area would be a start. And then we developed actually a roadmap. So in that case, we said the first thing is to read about the area, to familiarize yourself, then to reach out to people to collaborate with, and definitely be mindful that that there's a lot you can learn. And the recommendation is to listen to them quite a lot because they've worked in this problem area for quite a while and have a lot of knowledge that they can share. And then deeply collaborate with them throughout the project development.
To add another one, so that is definitely the using your skills in AI to do climate change mitigation and adaptation. That's one very important route. Another one is that many AI professionals are often in positions of power within society, for example, working for a large tech company that often has influence on policy decisions or basically represents a large group of people that is using AI technologies. And so using that systemic lever and systemic push to sort of drive change within a particular company or to get that company to shape it, to advocate for basically better climate action. It can be another different kind of lever.
Thank you very much, Priya. So speaking of companies, there's another question by Stephanie Henke asking, have you looked into the question of which actors, so which organizations, institutions are dominating the development of the landscape of AI and climate change? And how does it link to geopolitical power, large corporation power, such as industry player, the biggest tech companies in the world? You're all nodding, so please go ahead.
Yeah, very briefly. I mean, of course, some of the big tech companies are also one of the biggest players in this field. There's, of course, a lot of momentum also from research institutions, universities, and then as well as small tech companies and startups. But the large tech companies and their involvement could pose a problem, especially if, for example, public organizations outsource some of their analytics and some of their problem development to other companies. There might be dependencies that and those shifts in power that could arise from that, which is also hinted at in this question. I don't know if you others want to add something.
Yeah, I can weigh in a bit here too. So adding on to that, I think that one of the things that's really important to bear in mind if one is coming from an area outside of AI like policy, just realizing that AI is a kind of engineering. It is a tool. It's not something magical that only Google has access to and knowledge of. This is something that you really can do with experts in-house or with smaller players. And many of these tools are not something that only the biggest players do have access to. It's just that they are dominating the conversation because they're well known and they have a lot of power. but it's not because they need to be the players working here. And just sort of realizing that AI is not magic, demystifying that. It's very prosaic generally. And then also just bringing up how this ties in with oftentimes the particular parts of the world that have the most power here. So oftentimes this will lead to consolidation of power in particular parts of the world, and mean that, say, players in Silicon Valley are having too much control over what is happening in parts of the developing world, for example. And that is an imbalance that absolutely needs to be corrected.
Thank you very much. So we have a lot of questions coming in now. If there's a particular one you would like to answer next, tell me. Otherwise, I will just go ahead with the one by Molud Amazus. I hope I pronounced that correctly. Could you say a few words on the cost of AI-based solutions to reduce greenhouse gas emissions of large plants like pulp and paper, steelmaking, oil refinery?
So I guess very briefly, the two kinds of costs to consider in that context are often the actual cost of the algorithm and then the cost of, for example, instrumentation or process changes that need to be made in order to implement that algorithm. So without sort of deeper knowledge of, the steel industry, paper pulp industry, I can't necessarily comment on the second part, which is changes in instrumentation. In the case of the AI model itself, often in some ways software solutions have lower costs associated with them than hardware solutions. So I would really think that the sort of instrumentation and process changes would dominate in cost.
Thank you very much. And now we have a question on privacy by Sebastian Reible. He's asking, or he's saying first, it is often discussed that increasing households could be connected to smart energy grids using smart meters, probably also connecting electric. Now I lost my question again, sorry. Using electric cars to use them for distributed energy storage to better balance high energy production times and to retrieve energy in low production times. Is this technically feasible, and what impact on privacy and consumer protection, e.g. wear of batteries, could these technologies have?
I mean, there's a lot of work in progress, I would say, in that area. Those are valid concerns about privacy, for example. There are less intrusive and more intrusive methods that can be used, and there's definitely an ongoing direction in research to develop non-intrusive, non-privacy violating technology for the use in buildings, for example, for occupancy detection. So for example, one can use Wi-Fi distortion signals to detect if people are in the room, as opposed to installing a camera in the room, which would be much more intrusive. So this is a very cutting edge, ongoing area of research, of development. There's a lot of potential in these technologies, but they definitely need to be developed carefully, and all of these concerns need to be addressed.
And then to add to that, so it's sort of when we have decided that a particular application is worth it, then there's a lot of work and research, as Lynn is saying, to be done to figure out how to make that, the privacy considerations forefront. I think there's also a scoping question, which is really honestly balancing out these considerations of what is the particular benefit of a particular application and what are the privacy implications of that application, what is the data collection associated with that, and really asking questions about what data should we be collecting, what data should we not be collecting, et cetera, on that basis. These are often very difficult questions to answer. Often you're trading off between things like privacy and climate impact and equity, things that are not quantifiable on the same scale. And there are a lot of value judgments associated with that. But in general, that question of scoping is going to be a really important one as well.
I can jump in to answer a question about the NeurIPS session. So the workshop that we're hosting next week at the conference NeurIPS Will it be recorded for future viewing? Yes. And also, if you go to our website, you can see the recordings from our past workshops at last year's NeurIPS, also from our events at other conferences and events. So there are many videos available on our website from past events as well as from the upcoming one. I can also weigh in on the question by Antonias, would AI and ML training based on smaller data sets be a solution, and what are the main obstacles? So it's not going to fix everything, but certainly there are some certain cases in which training on smaller data sets could be useful, in particular in situations where, for example, there is less data available for certain parts of the world or for certain sectors, when it will be very useful to be able to still get some kinds of insights there. Some of the technologies that are being developed there, which are to some extent more in the research phase, are transfer learning, meta learning, few-shot learning. Those are all areas of active work in AI, and there's some amount of progress on that, but it's definitely something that I expect to see getting even better in the future.
Thank you very much, David. There's another question we haven't addressed yet. It's from Randall Bowie. Are you aware of any documented uses of AI in the biomass heating sector, more specifically to measure multi-generational industrial scale clearing and deforestation methods' impacts on biodiversity and ecosystems?
I mean, so I think what this gets at is measuring the changes in land use, and that can relate to biomass energy. And here, actually, the field of remote sensing is a main tool to measure these changes by way of satellite images, for example. And they have benefited really largely from machine learning in the past years. So machine learning has enabled better classification of images, has enabled object detection approaches in remote sensing. So this is really an area where there have been a lot of advancements, and measuring deforestation and illegal deforestation is one of the approaches here that's been pursued quite actively.
Thank you very much, Lynn. And now we have a question from Vago Gabor. What kind of concrete policies should the Greens suggest in the European Parliament regarding these topics? And we're very interested in that being a Green Foundation.
Lynn, would it be possible to reshare the slides on that for reference at the moment?
Yeah, I can do that. One moment.
While you're doing that, I can just quickly address one of the questions on assisting scientists of a specific field that want to use AI in their domain. The short answer to that is yes. It's really important when one's working in any of these areas to partner with the people in that particular area. And all of us are working with people who are expert in complementary aspects of these problems. I don't personally work on hydrology, but similar collaborations, yes.
Yes. And if the question was whether we specifically can aid, if you would like to reach out to us to help us try to make connections maybe to experts who do have insight on some of those, please do feel free to reach out.
So I pulled up the slides. I don't know if they're visible. Yeah. So these are the policy ideas we wanted to share in this talk. Again, there is a lot of need for policy in the whole pipeline of research, development, and deployment of such AI approaches. So there's really a tremendous need across the board. And I don't want to repeat everything here, but really, you need to facilitate interdisciplinary research. There need to be pilot projects that enable this technical readiness of these applications. And there also need to be an approach to understand how to deploy this in different relevant sectors and industries. And then what we also went into is how to regulate AI-driven technologies. And here, both classical climate change strategies are important, and things that are targeted at those emergent technologies that are driven by AI. And to understand how they impact the energy balance and how they actually can contribute to reducing greenhouse gas emissions. And then the last one set of recommendations that we had is how to leverage AI approaches in the public sector itself. And here it's really important to develop standards and an understanding of also what might be the side effects, what might be the pitfalls of applying AI in the public sector.
And to add to that, maybe one challenge in sort of us as academics getting more concretely into what is the specific policy that should be implemented is that it's often very context dependent, and it's also very sector dependent, and the number of sectors that are covered, for example, in the conversation on climate change is very wide. So for instance, that point on regulatory hurdles to deploying AI, the hurdles around how can a forecasting algorithm or a power system optimization algorithm be integrated into power system optimization processes, these sort of regulatory requirements around use of technology for power system optimization, integrating with existing processes, and sort of the interpretability of the subsequent applications. Those different kinds of regulatory hurdles look far different than the regulatory hurdles that may exist for incorporating AI into heavy industry or incorporating AI into agriculture. And so these are, in some sense, general broad principles of kinds of policies that we think are going to be really important to be thinking about. And we go into a little more detail in this in the briefing that will, I think, be posted in the chat after this. But again, we're also happy to chat further.
Thanks a lot. And now we have 2 more questions left over that go a bit in the same direction. So how would you get buy-in from private industry, cloud, AI, tech companies to implement changes of negative impact from AI, negative applications? That's one is from Rudy Rodriguez. And maybe at the same time, you could also answer the question by Spyros Vesurakis on how could large corporations be convinced to use AI and invest in AI tools for climate change risk assessment?
So I think that some of the ingredients here are awareness of the ways in which AI is being used and public demand, in addition to demand from within the AI sector specifically. So for example, there has been a very effective movement within the AI research community not to use AI in autonomous weapons systems. So there have been a lot of declarations that AI should not be used in various different applications. That has not happened as much in negative impact, in applications that have negative climate impact. And I would like to see more, more popular demand for not using AI in such contexts. But to some extent, this is also part of just the ways in which technologies are being used to accelerate different applications across the board. So I'm not sure it's easy to separate AI from that. To some extent, overall, the negative impact applications of all technologies should be considered from a policy perspective.
Yeah, maybe on that second point about risk from climate change. So these TCFD recommendations are about financial risks in companies, and there needs to be either a mandate or a business case, I think, usually to convince companies to take up something. So if it's worth for them to do it because they either mandate it to or because it's worth from a financial standpoint, then it will happen. So that's why policy is so important. Then maybe additionally, lots of the AI approaches require quite some institutional changes. So I think here also small proof of concepts could be helpful. So just like lowering the barrier to getting started on this, for example, could even be in an academic collaboration by having like a master's thesis written on that topic for the company. These kind of approaches can also help to get things started.
So to also kind of a point that applies to both of these things is that I think the way in which a lot of these topics are addressed in the public sphere and in the public conversation then shapes the kinds of pressure that are subsequently applied. So for example, when we talk about the impacts of companies, many companies will make promises about, you know, I'm going to be net zero by a certain year or something like that. And they're often talking about the impacts of their operations. They're not often talking about the impacts of their applications. And shifting the conversation to really demand holistic transparency from the entities that we wish to hold accountable, I think is going to be really important in, again, shaping that conversation and where the intention goes. And that, in some sense, is why we've tried to bring these three topics together in our presentation of AI for, again, climate change mitigation and adaptation on the positive side, but also on the other side, AI for applications that increase emissions potentially and the energy uses of AI itself, because in some sense, focusing an undue amount of attention on any one of those topics singularly, rather than sort of thinking about the systemic issue and how you balance these things and make sure to create regulation that is considering this entire system's context, misses part of the picture in a way that is potentially counterproductive. And so we should, in some sense, again, sort of demand that systems level thinking in general in our reporting, conversations, et cetera, about this topic in order to drive accountability and action.
Thank you very much. So I think we have one more question left that is unanswered by Vadim Kononenko. Could you expand a bit on whether AI could be helpful in bringing together environmental and social pillars of sustainability? Are there any examples to such use of AI?
I guess briefly, in a lot of the cases we consider, there is the potential for AI to facilitate applications that bring these pillars together, but the AI itself may not necessarily do that. So things that we think about like forest monitoring or biodiversity monitoring, they're very social. There are both environmental aspects to these issues of, you know, how you deal with forestry, how you deal with food access, all of these things. And there are also social aspects to those. So our recommendations for those applications is, you know, AI can be used to provide data, but in some sense, the data is only going to be useful if we use it to take action. And so in some sense, yes, AI can inform the bringing together of these pillars, but it is not going to be sufficient in doing that. There's really a lot of context around that that dictates basically whether these pillars will be considered together.
Thank you very much, Priya, and thank you very much to all of you for this excellent presentation and for answering those many, many questions. Thanks as well to the audience for posing all those questions. So I think my main takeaway for today is that AI cannot solve all the problems that our problem has these days, but it opens a lot of possibilities and is up to us how we use them. If you want to find out more about climate change and AI, there is an e-paper, and we will post the link to this into the chat right now so you can find it and read more. And you can check this out. So thanks a lot again to the panel and to the viewers, and I wish you all a lovely day.
Thank you, everyone. Thank you for inviting us.
Thank you so much.